In this video, we're going to talk about epsilon delta proofs. This epsilon delta, this is just a more rigorous way, very abstract way, to think about limits. It turns out that the limit as x goes to c of f of x equals L is the same as, given epsilon greater than 0, that there exists a delta greater than 0 such that f of x minus L is less than epsilon whenever 0 is less than x minus c, which is less than delta. Now, let's just get a better handle on what this means and on what that means. The left one says, if we remove the absolute value bars, it says what's in between the bars are in between negative epsilon and positive epsilon. If I add L to both sides, I learned that f of x is in between L minus epsilon and L plus epsilon. Now, if we ignore that this is bigger than 0. Now, absolute value is not always bigger than 0, regardless of what you think. It can be 0. Absolute value just can't be negative. There are three types of numbers: negatives, the numbers 0, and positive. The absolute value can never be negative, but it doesn't have to be positive. It can be 0. So we're excluding 0. If we just ignore that for a moment, this says that x minus c is in between negative delta and positive delta. And let's see. This means that negative delta is less than x minus c, and x minus c is less than delta. Oh, okay. I need a little bit more space anyways. X minus c is less than delta. But we want this to be less than 0. And we want this x minus c over here to be bigger than 0. This is what you get from the top one. This middle one is not exactly correct, because if you're in between negative delta and positive delta, you can be 0. And we do not want to allow x minus c to equal 0. Okay. Now, for whatever it's worth, okay. So, now adding c to both sides, x is bigger than c minus delta, and adding c to both sides, x is less than c plus delta, but bigger than c and less than c. We have these two pieces. Okay, wonderful. So now that we have a better handle on what these two statements mean, and whenever you have this one, whenever you have this one. Now, let us look geometrically at what on earth this means. So you have some graph maybe like that, call it f of x, and want to know what the limit is when x gets closer and closer to c. So by definition, f of x does not even have to be defined at c. It could be, it could not be, who knows. But at c, there's this open circle. Now, we claim that this is L. So what we do is we pick an epsilon neighborhood. Given any epsilon, we pick an epsilon neighborhood. that top piece is x plus epsilon. The lower piece is L minus epsilon. And if you were to take F for values, in between here, except at C itself, if you took F for values in between here, even up to the endpoints, you will end up in between there. Okay? Well, that doesn't really show that F for C is getting close to L. I mean, maybe F for C is getting close to that point, or that number, or that number. So what you do to show that you're wrong about it being at least some of those pink values I picked, you pick a smaller epsilon. So to the best of my ability, I'm going to try to draw the same exact graph and the same value for C. So straight across is L. And this is the same graph, f of x. Now, if I pick L a little bit smaller, then epsilon, a little bit smaller, then the upper limit will be L plus epsilon, L minus epsilon. Now, I guarantee you that if x is in this range, f of any one of these x values from here to here, except C, f of any of these x values will land in here. So for example, before, maybe remember up here I said, the limit can be that value, or the limit can be that value. Those values are now out here. My range got smaller. Well, you can argue again, hey, come on, why can't the limit be that number, or let the limit be that number? Yeah, absolutely right. You're absolutely right. Good going. So what I'm going to do is I'm going to draw the same graph all over again. I'm going to pick that point for C. And just like in the other graph, I really should have removed that one point at C. Should really remove the one point exactly at C. Okay, so now here is what we claim L is. We claim that L is right here. But now what we do is we pick a smaller epsilon. Remember, for any epsilon, you can find the delta, L minus epsilon. So now we have a pretty small neighborhood around L. And once again, I probably have C wrong, but we'll fix that. And we have the y-axis and the x-axis, and L plus epsilon. It's getting tighter, that neighborhood. That gives us this. And maybe the open circle for C is right there. That is, maybe C is there. Okay, so I have a tighter neighborhood. This little neighborhood is certainly smaller than that one. So now I know that f of any neighborhood in here, I know that f of any point in here, like that point, it will go to there. Anything in here, f of anything in here will be in this really small neighborhood of L. So, back to the last picture, please. That point can't be the limit anymore. That can't be the limit. This can't be the limit. That can't be the limit. But you know what? Maybe that point could. Maybe that point is still in here. Why can't that point be the limit? Or that point right there be the limit? You're right. Make epsilon even smaller. We're going to converge on L. That is what the delta epsilon process is. Okay, if you understood this, great. What you need to know, like you know your name. I learned this like immediately because I'm like, how am I ever going to remember this? And I'll remember this for the rest of my life. It's just words. It's just the saying. The limit as x goes to c of f of x equals L is the same as given any epsilon greater than 0, there exists a delta. And by the way, this delta is going to depend on epsilon. There exists a delta greater than 0 such that the difference between the y values, between f of x and L, is very small whenever x minus c is small and positive. Because we don't want x to be c. Remember, again, x minus c is less than delta. This means that x is in between c minus delta and c plus delta. But you know what? C is in between here. Here's c. You take a little away. You add a little to c. C is in here. Somehow we need to remove c. We don't want to talk about when x is c. Okay, that is why we say that it's bigger than 0. So you can say this and x is not c. But what that means is either x is in here or x is in here. X is in between c minus delta and c, or it's in here. X is bigger than c, but less than c plus delta. And you can actually equal the endpoints. Okay, said that twice now. So, like I said, let us do some limit proof, some epsilon delta problems. Suppose you are asked to prove the following. Prove that the limit as x goes to 3 of 2x plus 1 is equal to 7. Okay, so given any epsilon greater than 0, we must find delta greater than 0 such that the difference between the function and L, such that 2x plus 1 minus the limit, f of x minus L, is less than epsilon whenever 0 is less than x minus c. C is 3. X minus 3, which is less than delta. Now this is fairly easy. What's in the bars is 2x minus 6, which is 2 times x minus 3. So this piece here is exactly the same as this piece, which is exactly the same as that piece, which is exactly the same as this piece. Okay, so we want this to be true whenever x minus 3 is less than delta. Okay, how about we just choose delta to be epsilon over 2, because equal means that whenever I see this, I can write that. And I'm going to do that temporarily. If I put delta here, this is true whenever this is true. Yep, I'll believe that. No question about it. Okay, so what you do is, so let's put back epsilon over 2. So the proof is done because given any epsilon, I told you how to find delta. Given any epsilon greater than 0, I must find a positive delta. Now, just for the record, it does say that epsilon is positive, and if you take any positive number and you divide it by 2, it'll be positive. That is, delta will be positive. Now, let's see what is really going on here. F of x is 2x plus 1. Okay, all right. So pick an epsilon. And, okay, so c was equal to 3, right? Yeah, c was equal to 3. C is equal to 3. And I choose epsilon to be 1. That implies that delta is 1/2. Okay, let us see what's going on here. We're at 3. I go up to 3.5. I go up 1/2, and I go down 1/2. 2.5. Now, it's a line. As x gets bigger, y gets bigger. Okay, well, at 2.5, let me do it here. F of 2.5, well, you double x, you get 5, and you add 1. Okay, so f of 2, and let's first draw the line. So you have 1, and the slope is 2. There's the line, okay? And f of 3, the limit, it approaches 7. And I need to move this big times. Okay. Now, okay. So f of 2.5, f of 2.5 is 6. 5 plus 1 is 6. F of 3.5, you double it and add 1, it's 8. Let's do better than what I have here. So f of 3.5 is 8, and whether f of 3 is defined or not, it's right there, 7. Now, so this number is our 7 minus epsilon, which is 1, and this number is L plus epsilon. So I have my epsilon neighborhood, This is epsilon, and this is epsilon. And you know what? Remember, f of 2.5 went right to 6, and f of 3.5 went right to 7. So yeah, look at this. Everything in here, f of every one of these values will be in here. And that's all I wanted to show. If I give you an epsilon, I can find a delta such that f of c minus delta up to c plus delta, this will be contained in 7 plus minus 1, L plus or minus epsilon. Let's pick another epsilon. Now, this is really abstract, I understand this. We know that f of x is 2x plus 1, c is 3. Let epsilon be a quarter. So delta is half of epsilon in this case. So we claim, that's what we prove. It's an eighth. So let us see what is going on. So here is 3. I go to 3 plus epsilon, and I go to 3 minus epsilon. This is 2 7/8. This is 3 1/8. And we have our line. Well, f of 2 7/8 is here, and f of 3 1/8 is here. And since the function is getting bigger and bigger, it is true that f of everything in here, including the endpoints, f of everything in here will end up in here. But what are those values? What is f of 2 7/8? Well, when you double that, well, here, this is 23/8. When you double that, you get 23/4 plus 1, which I'll write that way. That's 27/4. This value is 6 3/4. This is 6, well, let's write it here. 6 3/4. Now, what's f of the upper region? What is f of 3 1/8? Well, if you double that, okay, this is the same as 25/8. 2 times that will be 25/4 plus 1. I write it as 4/4. Well, that's 29/4, which is 7 1/4. This is 7 1/4. But you know something? This is 7 minus 1/4, and this is 7 plus 1/4. Remember, the limit we claimed was 7, and epsilon is 1/4. So I can go up 1/4 and down 1/4. From 7, I can go up 1/4 and down 1/4. And look at how well it works. F of everything in here, including the endpoints, they land in here. Okay, if I make this width a little bit smaller, maybe instead of being this big, 1/4, maybe I make it smaller, well then I'll find a smaller neighborhood around 3. But the bottom line is, this is working nicely. Okay, let us prove another limit. Suppose you were asked to prove that the limit as x goes to 5 of 3x minus 2 is equal to 13. 3 times 5 is 15, minus 2 more is 13. So, given any epsilon greater than 0, you must find delta greater than 0 such that f of x minus L, an absolute value, is less than epsilon whenever 0 is less than x minus c, c is 5, is less than delta. Now, if I can get the left side to have this, then whatever it's less than, I'll call it delta. The left side is 3x minus 15, and this is less than epsilon. The left side is 3 times x minus 5, which is good because I want x minus 5 like I have here. This is less than epsilon, and this is the same as 3 times the absolute value of x minus 5 is less than epsilon. And here we go. This is the same as x minus 5 being less than epsilon over 3. And this doesn't change because we never really changed this. From here to the next line, all I did was say minus 2 minus 13 is minus 15. And to the next line, I factored out as 3. And then I used the fact that the absolute value of A times B is the absolute value of A times the absolute value of B. And since A was positive, I get the absolute value of 3 times the absolute value of x minus 5. But I know what the absolute value of 3 is. Okay, all right. So this statement is the same as that one, and this statement is like the one before. So all these statements on the left are true. So we want the left to be true whenever x minus 5 is less than delta. Well, just choose delta to be epsilon over 5. Okay, if I cross this out and I put delta, who in their right mind would say the absolute value of x minus 5 is less than delta whenever the absolute value of x minus 5 is less than delta? It's obviously true, and there it is. So if I give you epsilon to be 1/4, you should say, okay, delta is going to be epsilon over 5, which is 1/20th, which is 1 over 20. Okay? So since the limit is 13, here's some function, straight line or not, as x gets closer and closer to 5, we claim that x is gets closer and closer to 13. There's 13. Well, if you pick epsilon to be 1/4, so this number is 13 plus 1/4, and that number there is 13 minus 1/4. If you want to end up in that epsilon region, well then, apparently, okay, let me just fix the graph a little bit, if not a lot. If you take f of these numbers, I guarantee you that you'll be in between 12 and f of those numbers will be between 12 and 3/4 and 13 and 1/4. Now, just want to make one comment. It's pretty clear that the distance from here to here is bigger than the distance from here to here. This one's smaller. So that will make this 5 plus delta. This will not be 5 minus delta. But you know what? However big delta is, this is how big delta is. So I go the same to the left. That will be 5 minus delta. And if I take a smaller interval, if I just take f of numbers in here, well then, yeah, I'll end up in here. I mean, my goodness, when I took f of a bigger interval, I ended up in here. So if I take f of just a smaller one, I'll end up in there. Fair enough. I'll even end up in a tighter neighborhood or interval around 13. I'll end up in a tighter interval. I'll just be maybe in here. But nonetheless, I was able to find the delta. So please don't think that I'm saying that this whole interval has to be 5 plus delta and 5 minus delta. No. But a smaller part will be. In other words, if you have to be in here, and the left piece is much bigger than the right piece, well then, we will call this delta, and that will be 5 plus delta. And to the left, I'll only go up to here, because this distance is also delta. I'll be 5 minus delta. I guarantee you that f for stuff in here will land between L plus epsilon and L minus epsilon. I can say a stronger statement. I can say f of stuff from here all the way up to here will end up between plus and minus L plus epsilon and L minus epsilon. But that messes with the delta. I want it to be C plus delta and C minus delta. So I let C be the smaller of the allowable regions. Now when it comes to a line, yeah, you're never gonna have, 5 here and here and here. Okay, they're always gonna be equal, but when you have curves, that can change drastically. Okay, let us try another one. Suppose you have the limit as x goes to -2 of 4x plus 10, and this is equal to 2. Okay, so it's standard. Given epsilon greater than 0, you must find delta greater than 0 such that, learn that, such that f of x minus L is less than epsilon whenever 0 is less than x minus -2, which makes this plus 2 is less than delta. So somehow I want to get x plus 2 there. Okay? That's the whole goal. You need to memorize this. Understand it will be better. But once you have that, then you have 4x plus 8 less than epsilon. Then you can factor out the 4. 4 times x plus 2 less than epsilon. This 4 can come out as 4 times x plus 2 is less than epsilon. If I divide both sides by 4, then this is exactly this. Is less than epsilon over 4. Once I get this and this the same, then I just say delta equals that. So, choose delta the equal to epsilon over 4. Choose epsilon, delta the equal to epsilon over 4. Okay. How about this one? The limit as x goes to 5 of 2x plus 1 is equal to 11. Given epsilon greater than 0, you must find a delta greater than 0 such that f of x minus L, L is 10, the absolute value is less than epsilon whenever x minus c, and c is that number there, that c is less than delta. So we know the game, and something's bothering me already, and what's bothering me is that this limit is wrong, because 2 times 5 is 10 plus 1 is 11. So minus 11. So all I want to do is get what's in their absolute value bars to be x minus 5. Well, what's in it is 2x minus 10. But then I could factor out a 2 and smile, because now I have x minus 5. And then the absolute value of one thing times the absolute value of a product is the absolute value of 2, which is 2, times the absolute value of x minus 5. So the absolute value of x minus 5 is less than epsilon over 2. And all of this comes down whenever 0 is less than x minus 5, which is less than delta. So now we're done. We choose delta to equal that. Delta equals to epsilon over 2. And if you notice the pattern, so we've only been dealing with lines. When the slope was 2, we chose delta to be epsilon over 2. When the slope was 4, we chose delta to be epsilon over 4. If I did any other lines, when the slope was 3, delta should be epsilon over 3. Okay, so let's see where we went wrong here. Okay, so I did conclude this is epsilon over 3, but somehow when I wrote it, I copied it down wrong. And I am so glad that I didn't divide this by 5, because I would have gotten 1 over 20, because I went into this big geometric explanation. Okay, but when you divide this by 3, you get 1/12. So I just had a typo right there, nowhere else. Again, the slope was 3, and delta was epsilon over 3. So, you know, it's quite easy to know what the answer is going to be before you even do it. If I tell you that the limit as x goes to 7 over 13x minus 1, 7 times 13 is what? 91 minus 90. You're going to know that delta is epsilon over 13. And of course, if I gave you this, I hope of course, and it doesn't matter where x is going to 7, 9, it's going to be epsilon over 13. If I gave you 2/3 x plus a number, oh, how nice that worked out. This is going to be 3. We're going to know that delta is going to be epsilon over the slope, which is 3 over 2 epsilon. And if you have the limit as x goes to, I'll decide in a moment, okay, 5. X over 5 plus 1, which is 2, then we should know that delta is epsilon over 1/5, which is 5 epsilon. So if you're given a line, you know what the answer is. I'm telling you the recipe to get it. If this is a line, if this is a line, if this is a line, you know it. What more do you want? Okay, but what if it's not a line? What if it's not a line? Now it becomes a lot more interesting. Suppose you have the limit as x goes to 2 of x squared. Well, 2 squared is 4. So we need to prove that this limit is 4 rigorously. That is epsilon delta proof. Okay, so given epsilon greater than 0, we must find, given any epsilon greater than 0, we must find delta greater than 0 such that the function minus the limit, absolute value, is less than epsilon whenever 0 is less than x minus c, which is right here, that's 2, is less than delta. Now here's where we have problems. When I factor x squared minus 4, I almost smile because I get x plus 2 times x minus 2 less than epsilon. So I have the x minus 2, and this becomes the absolute value of the first times the absolute value of the second is less than epsilon. Now, I can't divide by this, because, I could, I absolutely could, as long as x is not negative 2. Oh, how convenient. X will never be negative 2. The problem is then I would get x minus, the absolute value of x minus 2 is less than this. But that doesn't tell me what delta is. Like, in other words, so now I say, okay, I'm done. That's delta. All right, very good. How about I tell you epsilon is 1? What is delta? You say, oh, no problem. Delta is 1 over, what's x? No. I'm only going to have to tell you what delta is. Given a delta, you must find, given an epsilon, you have to find delta. So I gave you an epsilon. Epsilon is 1, or it's 14, or it's 0.14. You can't tell me what delta is yet. So, no, it isn't as simple this time as just dividing by that leftover part. Leftover because you just want this. Okay. So, what we're going to have to do is bound delta. we're gonna have to bound delta. So we know this comes all the way down. This statement is whenever 0 is less than x minus 2 in absolute values is less than delta. So again, we want to find a bound on this. So what we do is the following. We choose delta to be less than or equal to some number. I would pick 1. You can use a half, you can use a million, you can use a quarter. Use 1. So this implies that x minus 2 is less than or equal to 1. That means x minus 2 is in between -1 and 1. Now, again, I want to get a bound on x plus 2 absolute value. That's going to motivate me like anything to add 4 to all 3 sides. So x minus 2 is in between 3 and 5. So what is the absolute value of x minus 2 less than? Well, if you have numbers between 3 and 5, what's the largest absolute value you'll get? 5. If you have the absolute value of x minus 2 is between -13 and 5, now here's 0. The absolute value of that number is going to be 13. The absolute value of that number will be less than 13. That number less than 13. That number 0. That number less than 5. That number less than 5. 5. So I would then say that the absolute value of x minus 2 will be less than 13. But for right now, we got 5. Okay, now this is excellent. This is excellent because, so we have this line. So now the absolute value of x plus 2 times the absolute value of x minus 2, well, we know that should be less than equal. Why? Because I said delta can equal 1. Okay, so we know that that 5 is at least as big as this, times x minus 2 in absolute value. Let's set this less than epsilon. And this is whenever 0 is less than x minus 2, which is less than delta. Now, here's where it all comes together. Now, this tells me that x minus 2 in absolute values is less than epsilon over 5. Whenever this. Okay, now, you have to be careful before you just say that, delta is equal to epsilon over 5. That wouldn't be true. For example, if delta is 7, epsilon is 7, this will be more than 7. More than 1. 7 over 5 is more than 1. But we claim that delta is less than 1. Okay, so we're going to take the minimum of epsilon over 5 and the number 1. So if epsilon is less than 5, that's going to be the least, and that's what you use. If epsilon is bigger than 5, you have to use 1. Okay, so let us see what is going on in this case graphically. Let us look at this carefully under a magnifying glass. So this here is y equal x squared. And here is 2. So whether this point is filled in or not, that's the limit which we claim is 4. Okay. Now, if I say, remember, if I say epsilon is equal to a half, then delta would be epsilon over 2 or tenths, which is less than 1. Okay. So, if I go up to 4.5, if I go down to 3.5, just for the record, this is 9/2, this is 7/2. I claim that if you go to 2 plus or tenths, 2.1, or if you go to 2 minus the tenths, which is 1.9, I claim that F stuff in here would lie in between. Now let's look at this carefully. What is 1.9 times 1.9? 81, 17, 1 times 19, I know, 361. What is 2.1 times 2.1? Well, 1 times 21 is 21. 2 times 21 is 42. It's 4.42. Okay. Now, this 3.5, why, that's 3.5. And this 4.5, that's 4.5. What I'm saying is that if you take F for stuff in between here, remember, the bigger number you square, the bigger results you get, if you're more than 1. Okay, I'm saying that F of this stuff lands in between not 3.5 and 4.5. It lands in between 3.61 and 4.42. Okay, so that's even better. Surprised though that one of the endpoints wasn't exactly right. Yeah. Okay, so I found the delta such that F for stuff in here not only wasn't that didn't take up the whole range of 3.5 to 4.5, but nonetheless it ended up in there. It ended up in there. Okay, so review these limits a number of times. Remember how easily you can do it when it's just a line. If you want to find the limit of a line as x goes to some value, I mean, just for the record, I don't see why we can't prove this in general. What is the limit as x goes to c of mx plus b? Well, this is going to be mc plus b. This is going to equal to mc plus b. Okay. Now, given any epsilon greater than 0, we must find delta greater than 0. And delta, oops, that's not how you write delta. Delta is supposed to equal to epsilon over the slope. We want to find delta greater than 0 such that the function mx plus b minus the limit mc plus b in absolute values is less than epsilon whenever 0 is less than x minus c, which is less than delta. Well, if you have plus b and you're subtracting, they cancel. So now what's left is mx minus mc. We can factor out the m from there. So I do have one error. It should be over the absolute value of m. So what I said earlier just worked only because our m's were positive. I can factor out an m. This is less than epsilon. Now I can factor the m out from the absolute value. And then it all comes together. M minus c is less than epsilon over the absolute value of m. And this must be true whenever this is true. Now, I ran out of board space. I can't scroll down anymore. So I'll write my answer here. Choose delta the equal that. Delta should be epsilon over, not the slope. I apologize. But the absolute value of the slope. Okay, this completes the video on epsilon delta proofs.